Welcome back to the deep dive. Today, we are taking a pretty monumental step. We are leaving the comfortable, contained, finite world of discrete events. The world where we can count outcomes on our fingers, like the face of a die or the result of a coin flip.
That's right. We're stepping out of that clean, sort of laboratory setting of ideal experiments and into the messy, dense, and continuous reality of technical measurement. If you are dealing with a measurement that involves, say, time or distance, temperature, voltage fluctuation, anything that lives on a continuum, you're no longer counting possibilities. You're dealing with a vast, unbroken span of outcomes.
And here's the problem, right? The robust mathematical foundation we built for our comfortable discrete world, it suddenly gets stretched to the breaking point when we face the true, unrelenting nature of infinity. We thought we had the rule book for probability, but when we tried to apply it to real numbers, the mathematics failed. Instantly and quite dramatically.
So our mission today is a deep analysis of how the entire concept of probability had to evolve. We're going to map out the mathematical generalization required to handle these continuous complex phenomena.
It's a comprehensive deep dive into what mathematicians formally call general probability spaces.
We're basically providing you with the necessary shortcut to understanding the why behind this huge mathematical leap, particularly the introduction of things like sigma additivity and the measure space concept. Now, this material is rigorous, we know that, but we promise to make the path as clear and as painless as possible.
Let's begin by quickly reviewing our solid ground. For those finite outcome sets, our foundation was built entirely on the three famous Kolmogorov axioms, named after Andrei Kolmogorov, who codified the system back in the 1930s.
Okay, so let's unpack that finite foundation. What were the basic building blocks we used to define probability back then? Well, we started with the outcome set, omega, which just lists all possible results. So for a die, it's 1, 2, 3, 4, 5, 6. And crucially, we assume that every single possible subset of outcomes, what we call the power set, P of omega, could be assigned a probability. P, the axioms simply ensure that this assignment is rational and, consistent.
And the first two axioms, K1 and K2, they seem to be universally accepted truths, right? They feel obvious.
They are beautifully intuitive, and they're non-negotiable even when we move to infinity. K1 is non-negativity. The probability of any event A has to be greater than or equal to 0. You can't have a negative chance of rain. And K2 is normalization. The probability of the entire outcome space, P of omega, must be exactly 1. Something must happen when the experiment is run.
Right. If I throw a six-sided die, the chance that some face turns up is 100%. Simple enough. And K3 was our rule for combining those outcomes.
K3, in the finite world, is finite additivity. It just states that if you have two events, A and B, that are mutually exclusive, meaning they can't happen at the same time, they're disjoint, then the probability of A or B happening is simply the sum of their individual probabilities.
Yeah.
P of A union B equals P of A plus P of B.
So that three-part structure, the outcome set omega, the power set P of omega, and the probability measure P satisfying K1, K2, K3, that define the finite probability space. And it worked flawlessly for centuries.
It did. But now comes the critical moment. We have to venture beyond the finite. When we move out of the lab and into the real world, we hit infinity. And we need to be incredibly careful because, as mathematicians quickly realized, infinity is not a monolith.
You introduced the core challenge here. We have two fundamentally different kinds of infinity we have to tackle, and they demand different rule books.
Yes, case 1 is the countably infinite. Think of the natural numbers, 1, 2, 3, 4, and so on forever. The list is endless. But we can, in theory, put these elements into a one-to-one correspondence with the natural numbers. We can number them.
The classic examples of this kind of infinity improbability are sequential processes, right? Like counting the number of throws until you get a heads, or counting the discrete number of atom decay events. The count never ends, but each event is a distinct listable step.
Exactly. And then there's case 2, the much, much trickier one, the uncountably infinite. This is the realm of the real numbers. If you're measuring a temperature, that temperature can be 20 degrees, 20.1, 20.000000000001, and so on. It's a dense continuum. You can't number the elements because between any 2 points, there is an infinite, unlistable number of other points.
And that sheer unforgiving density of the continuum is precisely where our beloved K3 finite additivity completely fails.
Correct. So we approach this challenge systematically. We'll start with the gentle entry point,
Yeah.
the countable case.
Okay. So we're still in the world where we can number our outcomes, even if that list stretches on forever. We have our outcome space omega, which might be the natural numbers n. What happens to our three Kolmogorov axioms now?
Well, in this countably infinite context, we get to keep our system of events, the power set. That part is fine. And since we're just dealing with a sequence of outcomes, the core concepts of non-negativity, K1, and normalization, K2, are perfectly stable. They still hold.
But K3, the finite additivity rule, which only covered the union of two events, that's now insufficient. We might need to combine an infinite sequence of events, A1, A2, A3, and so on, to calculate a single probability.
And that is the crucial mathematical step we have to take. We must replace K3 with a more powerful axiom, K3 star, which we call sigma additivity. The name itself gives you the clue. The Greek letter sigma, in this context, explicitly refers to an infinite summation.
So tell us exactly what K3 star, this sigma additivity, demands.
It demands this. If we have an infinite sequence of pairwise disjoint events, A1, A2, A3, and so on, meaning no two events overlap, the probability of their union, so the chance that any one of them occurs, must be equal to the infinite sum of their individual probabilities. P of the union of the AI equals the sum of the P of AI.
This sounds, I have to say, intuitively obvious to a non-mathematician. If I can add up two probabilities, why can't I just say I can add up 3, 4, 5, and eventually infinitely many? Why did mathematicians have to explicitly write this down as a new rule?
That's a great question, and it gets right to the heart of mathematical rigor. Finite additivity only guarantees consistency for any fixed, finite number of events. It tells us nothing about the behavior when that number goes to infinity. When we move to infinity, we're dealing with limits and convergence. Without K3 star, our system is unstable. Finite additivity just doesn't guarantee that the resulting probability measure will be consistent when you're dealing with infinite limits. K3 star acts as the mathematical, let's call it winterproofing. It ensures that when we calculate critical results in stochastics like expected values over an infinite time horizon, or checking if an infinite process converges to a stable state, the probability measure remains non-contradictory. It's the structure that links the finite rules to the infinite sums we need for countable spaces.
That makes sense. We need a specific rule that guarantees the mathematical structure stabilizes at the limit. Okay, let's see this in action. Let's try to verify an abstract measure. We'll define our outcome space, omega, as the natural numbers, n, and we'll define the probability of any subset A as the sum of 1/2 to the power of n for every n in that set A. So, for example, if we were measuring the chance of an event happening on the 3rd, 5th, or 10th try, we'd add 12 cubed plus 12 to the 5th plus 12 to the 10th.
Right, and our mission is to check K1, K2, and K3 star. K1, non-negativity, is immediate. Since 1/2 is positive, any sum of 12 to the n has to be positive. So check.
Okay, K2, normalization, forces the infinite calculation. To find P of omega, we have to sum the probability of all natural numbers. That is the infinite geometric series. The sum from n equals 1 to infinity of 12 to the power of n.
And this is a classic test. Since the base q is 1/2, which is less than 1, we know the series converges. We just have to rely on the formula for a geometric series starting at n equals 1, which is q divided by 1 minus q.
So plugging in q equals 1/2, we get 1/2 divided by 1 minus 1/2. That's 1/2 divided by 1/2, which is 1. The total probability of the entire space is exactly 1. K2 checks out thanks to the convergent nature of the infinite series.
In K3 star, sigma additivity holds because the series we're summing, 12 to the n, is absolutely convergent. This means that if we partition omega into an infinite sequence of disjoint sets, the AIs, the total sum of their probabilities is simply the result of rearranging the terms of the grand overall series. Absolute convergence guarantees that rearrangement doesn't change the total sum. So this confirms this abstract definition creates a valid, countably infinite probability space.
Now, let's apply this mathematical success to a concrete situation, the infinite dice roll.
This is a perfect demonstration of K3 star. Imagine rolling an ideal six-sided die repeatedly until the first 6 appears. Our outcome space omega is n. The first 6 could be on the first throw, second, third, or even the 1,000th.
This follows what's called the geometric distribution. We define the elementary probability P of ISO. The first 6 falls exactly on the I throw.
Right, and for the first 6 to appear on the I throw, you need I minus 1 failures, followed by 1 success. The probability of failure, not a 6, is 56. The probability of success, a 6, is 16. Therefore, P of I equals 56 to the power of I minus 1 times 16.
Okay, so here's the practical question that demands K3 star. What is the probability that the first 6 falls on an even throw? We're looking for the union and the second throw, the fourth throw, the sixth, the eighth, and so on, infinitely. Since these events are all disjoint, sigma additivity tells us we have to calculate the infinite sum of their individual probabilities.
We need to sum P of I, where I is 2, 4, 6, 8, and so on. We can write this as a sum over a new variable, k from 1 to infinity, where I equals 2k.
Okay. Let's put on our algebra hats and walk through this slowly because auditory calculation of a geometric series requires some careful steps. We are calculating the sum from k equals 1 to infinity of 56 to the power of 2k minus 1, all times 16.
Right, and that term, the 56 to the 2k1, that's what makes it tricky.
Yeah.
We need to isolate a term raised simply to the power of k.
My algebra is feeling a little rusty here. We have 2k minus 1 in the exponent. How do we separate that so we can see the base, our q, clearly?
We use the exponent rule x to the power of a minus b is x to the a times x to the negative b. So we can rewrite 56 to the 2k1 as 56 to the 2k multiplied by 56 to the negative 1.
I see. And 56 to the negative 1 is just the reciprocal, which is 65.
Exactly. So we have 56 to the 2k times 65, all multiplied by that original 16, which was defining the probability of the final successful throw.
Okay, now we can pull out the constant factors, the things that don't depend on k. The constants are 65 and 16.
And when we multiply those two together, 65 times 16, the 6's cancel out, we're left with just 15 as a constant multiplier outside the infinite sum.
Okay, that cleans up the outside. The equation now looks like this. 1/5 times the sum from k equals 1 to infinity of 56 to the power of 2k. Now for the inside of the sum, 56 to the 2k. I can rewrite that as 56 squared, all raised to the power of k.
Precisely. And that gives us our clean base, q. Since 5 squared is 25 and 6 squared is 36, our new base q for the geometric series is 25 over 36.
Great. Now we just apply the formula for the sum of a geometric series starting at k1q divided by 1 minus q.
The denominator is 1 minus 25 36. So 1 whole, or 36 over 36, minus 25 over 36 is 11 over 36.
So the sum of the series itself is 25 over 36 divided by 11 over 36. The 36's cancel out, leaving us with 25 over 11.
Almost there. We have to remember the factor we pulled out in the beginning, the 15.
Right. Final step. We multiply 15 times 25, 11. The 5 on the bottom cancels into the 25 on the top 5 times. And the final exact probability is 5 over 11.
That's 511, or roughly 45.45%. This result demonstrates the profound necessity and really the power of sigma additivity. We successfully added an infinite list of disjoint probabilities to get a finite, consistent answer.
This calculation really demonstrates the success of the countable case. As long as you can number the events, even if that sequence is infinite, the tools of sums and series backed by sigma additivity work perfectly. We are mathematically safe.
But that safety, it stops right here. That success was achieved because, even though the sequence was infinite, the elements were still discrete and listable. Now we move into the domain of the uncountable continuum, where we can no longer number the elements, and that is where the rules break down entirely.
So we are now in the continuous realm. The real numbers are. We're measuring voltage, observing time duration, recording temperature. And the sources warn us that if we try to apply the same strategy here, defining probability on the entire power set of R, we run into an inescapable contradiction.
The problem is the sheer unimaginable magnitude of the power set of R. It is mathematically, it's just too vast. It contains what are called wildly constructed sets, or what we might call pathological sets, which behave so erratically that trying to assign a consistent probability measure to every single one of them leads to inescapable logical contradictions.
Let's focus on the paradox that arises from this, which really hinges on the probability of a single point. This is the point paradox.
In any continuous distribution, be it voltage, weight, or time, what must the probability of hitting exactly one single specific point x be? Say, the probability of a bus waiting time being exactly 5.000000000, and so on minutes.
Well, in a continuum, if every point had some positive probability, the sum of all those infinite probabilities would immediately be infinite, right? And that violates normalization, K2, where P of omega has to be 1. So the probability of any exact single point x must be 0. P of the set x equals 0.
This makes perfect sense in practice. Think back to our flower factory quality control example. Engineers and scientists are only ever concerned with intervals. They'll ask, what is the probability of the bag weighing between 990 grams and 1010 grams? They never ask for the probability of 1,000.000000 grams exactly.
And this leads to a critical implication, which we can call property n. Because the individual points have 0 measure, the boundary points don't matter in the continuum. The probability of a closed interval AB is the same as an open interval AB. The single points at A and B contribute exactly 0 to the overall measure.
Now, here is where the math explodes, because we combine that 0-point property n with our powerful new tool, sigma additivity, K3 star.
The entire set of real numbers R is, by definition, the union of all its single points. It is the union of union by 1, union by 3, and so on for all real numbers x.
Right. So if we try to define probability on the entire power set, and we use K3 star, which we have to deal with infinite sequences, we run into this paradox. We establish that for every single point x, the probability of x is 0. If we apply sigma additivity, the probability of R should be the infinite sum of the probabilities of all its single points. So this means we are summing an uncountable infinity of zeros.
Mathematically, that looks like the sum over all x in R of px, which is
Okay.
just the sum of a bunch of zeros, and that sum has to equal 0.
But wait, we must satisfy K2 normalization, which dictates that the probability of R has to be 1. So we have a catastrophic breakdown. 0 does not equal 1. The system's fundamental contradictory.
That is absolutely profound. In the countable case, we summed a sequence of non-zero numbers and got 1. In this case, even though we have an infinity of zeros, they can't add up to 1. What makes the uncountable sum of zeros so different from a countable sum?
The difference is listability. In the countable case, back in part 1, when we summed 12 to the n, the series converged beautifully to 1. But even in a countable case where all the individual p of I were 0, the countable sum would still converge to 0. The rules of summation hold for countable lists. The problem with the real numbers is that the set of points in R is so dense that it defies the fundamental structure of infinite summation entirely. You can't just use the list-based K3 star rule on an unlistable set. When we try, we expose the underlying flaw in assuming the entire power set is measurable.
And this wasn't just some tough math problem. This is a mathematical crisis in the early 20th century.
It was. This logical contradiction was formally demonstrated through the impossibility theorem by two mathematicians, Stefan Banach and Kazimierz Kuratowski, back in 1929. They proved, definitively, that those four desired properties, non-negativity, normalization, sigma additivity, and the zero probability of a single point, cannot coexist if you demand the measure covers the entire set of all possible subsets, the power set of R.
So the very foundation of probability was broken when applied to continuity. If the power set is the source of the contradiction, then the conclusion is unavoidable. We have to retreat. We have to become more cautious, more selective about which subsets of R we even allow ourselves to measure.
Exactly. We have to filter out the pathological sets that lead to these impossible results.
Okay, so if using the entire power set of the real numbers is mathematically intractable, we need a Goldilocks system. We need a system that is selective enough to fulfill the axioms without contradictions, but also rich enough, extensive enough to cover every practical application we need, like measuring the probability of any interval or combination of intervals.
This is the genius of Émile Borel's solution, which was later formalized by Henri Lebesgue. The Borel sets provide that perfectly balanced restricted rulebook.
So how do we build this structure? We can't start with the whole power set, so where do we begin?
We start with the building blocks we know are absolutely essential for practical measurement, the intervals. Specifically, we define a tiny foundation, a basis set I, as the collection of all half-open intervals, AB, open on the left, closed on the right. This is our starting point, our property B0.
Why half open? Does that precise definition matter?
It matters for consistency and mathematical simplicity, but the exact starting configuration, whether you use all open intervals or all closed intervals or half open, it doesn't change the final resulting structure. The three stability rules we're about to impose will automatically generate all the other types of intervals anyway.
Okay, so we have our starting wish list, all half-open intervals. Now, we don't allow just any random set into our new restricted system, which we'll call the event space A. We impose three non-negotiable laws that define a sigma algebra.
These three laws are the stability rules. 1, B1, total space. The system must contain the whole outcome space, R2. B2, complementation. It must be stable under complementation. So if a set A is in the system, its complement, R minus A, must also be in the system. If you can measure the chance of something happening, you must be able to measure the chance of it not happening.
That makes sense.
And 3, B3, countable union. Crucially, it must be stable under countable union. If you have an infinite sequence of sets, A1, A2, A3, and so on that are all in the system, their union must also be in the system. This reintroduces our necessary K3 star rule, not just for the measure P, but for the domain of events itself.
And the result of applying these stability rules to our starting point, the half-open intervals I, is what we call the Borel sigma algebra, BI. The mathematics guarantees that the smallest possible structure, the minimal hull that contains all our intervals and satisfies B1, B2, and B3 always exists.
This minimal hull concept is key. We are not grabbing the whole tower set. We are taking the smallest possible set of events necessary to guarantee consistency and cover the intervals we care about.
What's truly amazing is how these simple rules generate such a vast collection of usable sets. It's like a kind of mathematical avalanche. We only threw in half-open intervals, but suddenly the system gives us everything we need for practical application. Let's see how that works.
Okay, first, consider unbounded intervals, like minus infinity to x, closed at x. We can construct this by taking the countable union of half-open intervals that stretch to the left. For instance, the union from n equals 1 to infinity of x minus nx. Since we are allowed countable unions by rule B3, this unbounded interval is immediately included in the Borel system.
And once we have that, the interval from minus infinity to x, rule B2, complementation, instantly gives us the opposite, the interval from x to infinity, including x. Since the complement of a measurable set must be measurable, unbounded closed intervals are in.
Now, let's construct a standard closed interval, AB, which includes the boundary points A and B. We can construct this by taking the entire real number line, R, and removing everything that is strictly less than A, and removing everything that is strictly greater than B.
Wait, so removing everything less than a means removing the interval, minus infinity, A, and removing everything greater than B means removing B infinity. Both of those are already Borel sets because their complements are countable unions of our initial half-open intervals.
Exactly. Since the Borel system is stable under complementation and finite intersection, AB is constructed just by combining the complements of sets we already know are Borel. Therefore, closed intervals are guaranteed to be Borel sets.
Okay, now for the final and perhaps trickiest construction, the open interval, AB. This one excludes both A and B. We can't just define it as a simple complement or difference of the unbounded sets we used before because we are constrained by that countable union rule, B3.
This is where we have to use the limiting process. We define the open interval, AB, by taking an infinite union of closed intervals that slowly inflate or squeeze in toward the boundaries A and B without ever quite touching them. We use the sequence of closed intervals, A plus 1 over n, B minus 1 over n, where n is a natural number running from 1 to infinity.
So when n is 1, we have a plus 1, B1. When it is 100, we have a plus 0.01, B0.01. The interval is getting wider and wider, pushing closer to A and B.
Right, but since 1 over n never reaches 0, it only approaches it as n goes to infinity. The sequence of intervals perfectly fills the open space, AB, but mathematically excludes the boundary points A and B.
And because we're allowed to take the countable union, that's rule B3, of these growing already established closed intervals, the open interval, AB, is guaranteed to be a Borel set.
This is the crucial takeaway for you, the listener. The Borel system contains all intervals open, closed, half-open, and unbounded combinations. It contains everything we need in science and engineering to define a practical region of measurement. But, and this is the key, it is restricted enough to avoid those pathological sets that cause the Banach-Krotowski paradox.
So the system works. It's both functional and contradiction-free, and this leads us to the formal definition we were aiming for all along.
The combination of the outcome space, in this case the real numbers R, and this newly constructed system of measurable sets, BI, the Borel sigma algebra, is called a measure space.
I really like the empty vessel metaphor for the measure space, our BI. It's the structure domain. It's the pre-approved list of events we're allowed to assign a probability to without risking logical inconsistency.
Exactly. It has the stability rules, B1, B2, B3, baked into its structure. Only now, after we have established this stable domain, do we define the probability measure, P. We define P specifically on BI, not on the whole wild power set.
The final structure, then, the ordered triple R BIP, is the formal probability space 2R. By restricting our domain to the Borel sets from the start, we successfully bypassed the mathematical impossibility and created a solid foundation for continuous stochastics. The solution we just mapped out, the construction of the Borel sets, was specific to the real numbers, using intervals as our necessary starting block. But probability needs to be universal. What if our outcome space, omega, isn't a number line, but a complex set of functions or states in a highly abstract system?
If omega is an abstract, uncountable space, we need to generalize the concept of the Borel sets. We generalize it to the sigma algebra, which we'll call A.
This is the truly abstract part, but it's essential because it unifies all of modern probability theory, making it applicable absolutely everywhere.
We formally define a sigma algebra, A, on any non-empty set omega by simply enforcing the three abstract stability criteria we learned when building the Borel sets. We often call them O1, O2, and O3 in the abstract context. O1. The total space omega must be an A. You have to be able to measure the universe of possibilities, O2. Complements. The system must be closed under negation. If A is in the system, then its complement, AC, must also be an A. And O3, countable unions. System must be closed under infinite union. If A1, A2, and so on are an A, then their union must also be an A.
So the moment a set system A meets these three conditions, it's a sigma algebra. The Bohr-Paulets are simply a special case of a sigma algebra that was generated by the intervals on R. I want to pause and offer an analogy here. The sigma algebra is essentially our legal framework for measurable events. If an event doesn't pass these three laws, the law of total space, the law of complementation, and the law of countable combination, we legally cannot assign it a probability. It is unmeasurable within the consistent rules of our system.
That's an excellent way to put it. This legal framework is what gives us the ability to use the calculus of probability, the integrals, the limits, without fear of contradiction.
This brings up the crucial concept of generating the smallest measurable hull. In an abstract problem, we might have a specific set of events. F, we want to measure, say, specific system states or conditions. That wish list F is rarely a valid, complete sigma algebra on its own.
Right. It's incomplete. Maybe it only contains single points but not their complements, or maybe it contains finite unions but not infinite ones. We then construct the smallest possible set system that contains every element of F and also satisfies the three stability rules.
And this minimal hull is the sigma algebra generated by F. It's the mathematical equivalent of saying, here's the short list of things we care about. Now, what is the absolute minimum framework we need to build around them to make the whole structure mathematically valid and closed?
And the mathematics guarantees that this smallest consistent structure always exists, regardless of how complex our initial outcome space, omega, or our starting wish list F, are.
By building this minimal, stable structure, we are ensuring that we have a contradiction-free domain for our probability measure before we even define the measure itself. We've done all the preparation work to guarantee consistency.
And this brings us to the culmination of our deep dive. The final, abstract, universally applicable definition of the abstract probability space. It is the ordered tripel, omega, AP. Omega is the outcome space, whatever physical or abstract reality it represents. A is the sigma algebra, the defined set of measurable events that adheres to the three stability rules. And P is the probability measure defined only on A, which satisfies K1, non-negativity, K2, normalization, and K3 star, sigma additivity.
This abstract framework is the bedrock. Whether you are modeling the finite throw of a physical die, where A is the power set, the largest possible sigma algebra, or you're analyzing complex stock price movements over continuous time, or grappling with the inherent uncertainties of quantum mechanics. Formally, you are always operating within an abstract probability space, defined by this robust, consistent omega AP triple. #tag outro. So what does this entire mathematical journey mean for you, the learner? Let's synthesize the necessity of this profound structural shift. We started with K3, finite additivity, which worked for discrete finite outcomes.
When we encountered countable infinity, the natural numbers, we needed the stronger K3 star, countable sigma additivity, to ensure convergence and stability of infinite sums.
But the true challenge arrived with the continuous, uncountable real numbers. That incredible density forced us to confront the fact that we could not simply measure everything. The power set was deemed impossible because it immediately led to the impossible paradox where an uncountable sum of zeros had to equal 1.
And the crucial step, the leap into modern probability theory, was recognizing that to calculate probability in continuous spaces, you must first define the measure space, omega A. You must construct that restricted, well-behaved set of measurable events, the sigma algebra first.
Going back to our flower factory analogy, the power set of R was too full of theoretically broken subsets that the engineers would never use. The Borel sigma algebra filters out those flaws and only provides the set system intervals and their combinations that we need for practical, contradiction-free measurement. This structure is mathematically necessary and really life-saving for consistency in complex problems involving limits and continuity.
And finally, a provocative thought to leave you with, one that extends beyond the immediate needs of engineering and finance. We use the Borel sigma algebra because it is rich enough to contain every event we could ever practically need.
But the very existence of the Banach-Krotowski impossibility theorem proves something deeply unsettling about the limits of mathematics itself.
It implies that if we had not restricted ourselves to the Borel sets, the power set contains vast numbers of theoretical sets that are truly unmeasurable. These are sets that simply cannot be assigned a probability, a length, or a volume without violating the fundamental rules of mathematics. They are not just hard to measure. They are mathematically impossible to measure consistently within our axiomatic system.
So while you will likely never encounter one of these truly unmeasurable sets in your work, their existence reminds us that the structure of the infinite continuum is often beyond our complete logical grasp, and that abstract mathematics is constantly pushing the boundaries of what can be consistently quantified and understood.
A fascinating concept to ponder indeed. This foundational structure we've mapped out, the abstract probability space, is what allows statisticians and physicists to continue building sophisticated models without having to worry that their entire house of cards will collapse due to an underlying logical contradiction.
That's all the time we have for this deep dive into sigma additivity and the measure space. We hope you now have a much clearer understanding of why your complex equations need that robust abstract foundation. Thanks for diving deep with us. We'll be filling these abstract spaces with life and concrete distributions next time.